So, uh, have you ever noticed how a company can have this like absolutely brilliant, world-changing business strategy on paper, but then it just completely falls apart on the actual factory floor?
Oh, yeah. I mean, it happens all the time. It's almost a given at this point.
Right. Like you see the glossy press release, the CEOs on television talking about, revolutionizing the entire industry, and the stock price surges.
And then reality hits.
Exactly. Then you actually try to buy the product, and it's delayed by 6 months, or it finally arrives, and the quality is just totally unhinged.
Or those groundbreaking features they promised just physically aren't there.
Yeah, we see this constantly with tech startups, automotive companies, even like massive global clothing brands.
Absolutely.
So why is there so often this glaring, seemingly insurmountable disconnect between the visionary boardroom and, the gritty reality of the assembly line?
Well, that disconnect is basically the classic corporate tragedy of our modern era. It is this vast, treacherous gap between the what and the how.
The what being the vision, right?
Right. I mean, a CEO can dictate what they want to happen from a boardroom. But the how involves, millions of moving parts, thousands of human beings, and just unforgiving physical limitations.
And bridging that gap is arguably like the most difficult challenge in global commerce today, which is exactly what our mission is for today's deep dive.
It's a huge topic.
It really is. So for everyone listening, we're going to crack open a stack of incredibly detailed source materials focused entirely on functional and operational strategies.
Which is really the hidden architecture of the entire physical world around us.
Yeah, it's basically the playbook that dictates why your phone was assembled in a specific way, why certain cars take a year to deliver, and why some companies survive massive supply chain disruptions while others just completely fold.
And, the material we're pulling from today is foundational for anyone who wants to understand the mechanics of global industry.
Right. Whether you're actively managing a supply chain or you're just a curious consumer wondering why your online orders are suddenly getting cheaper or like taking way longer.
Exactly. Understanding these operational strategies is, well, it's basically the ultimate cheat code to understanding business.
I love that. A cheat code.
Because it's not just about what companies decide to build, it's about the intricate, deliberate logic behind how they choose to build it.
Every delayed package, every incredibly cheap gadget, every customized order you make online, it all traces back to a series of high-stakes operational decisions.
It really does.
So let's start with this fundamental concept that seems to cause so much confusion: operations strategy.
Yes, let's define that.
Because I hear this term thrown around in corporate meetings all the time, often interchangeably with just like basic management.
Which is a huge mistake.
So to clear the air right out of the gate, what actually separates an operations strategy from just, managing the people making the stuff?
It's a critical distinction, and honestly, blurring the two is usually where companies take their very first fatal misstep.
Really? Just mixing up the terms.
Well, mixing up the mindsets. Let's
Yeah.
look at the hierarchy, right? At the very top, you have the overarching corporate or business strategy. This is the grand vision.
Like, we're going to be the most affordable, globally accessible furniture brand in the world.
Perfect example. Beneath that, you have functional strategies for the various departments.
Okay, so marketing says, here is how we advertise cheap furniture globally. Finance says, here's our capital structure to support low margins.
Exactly. And then production or operations has to figure out how to actually make that furniture cheaply.
Right, the actual physical work.
Yes, but this is where we really have to separate operations strategy from operational management. The source material draws a very hard line here.
Right, walk me through the difference.
Operational management is the day-to-day grind. It's the manager on the floor on a Tuesday morning realizing they're short on pine wood, right?
Oh, okay.
So they have to reassign 3 workers to a different machine just to keep the line moving. It's immediate, it's tactical, and it's highly reactionary.
So it's basically the actual sweating on the field. Like calling an audible at the line of scrimmage because the defense shifted.
I love that analogy. Yes, exactly that. Operations strategy, on the other hand, is designing the playbook years before the game is even played.
Years before, wow.
Yeah. The material defines it as the total pattern of decisions that shape a company's long-term capabilities.
Okay, so it's much bigger picture.
Right. It has 3 distinct characteristics that separate it from daily management: a much longer time frame, a significantly broader perspective, and a higher level of focus.
So an operations strategy isn't asking, do we have enough wood for Tuesday?
No, not at all. It's asking, over the next 5 to 10 years, should our entire global manufacturing base transition from wood to advanced sustainable composite materials?
Oh, wow. That's a massive question.
And then if so, what kind of entirely new factory ecosystem do we need to literally invent to do that?
Man, that makes the stakes incredibly high. I mean, if you get the daily management wrong, you miss a shipment.
Right, a temporary hiccup.
But if you get the operations strategy wrong, you build a billion-dollar factory that produces something nobody wants, or produces it in a way that just bankrupts you.
Which is exactly why the strategy cannot be developed in a vacuum. You can't just brainstorm it in a locked room.
So how does a company actually figure it out?
Well, the sources visualize this beautifully. Imagine the operations strategy sitting right in the center of a tense, four-way tug-of-war.
A tug of war. Okay, I'm picturing it.
There are four distinct forces constantly pulling and pushing on it, and a successful company has to balance all of them simultaneously.
Okay, I want to walk through these four forces because I suspect this is where most of those boardroom to factory floor disconnects actually happen.
You would be absolutely correct.
So what is the first force weighing down on the strategy?
The first, coming from the top down, is the corporate strategy itself. The ultimate North Star, like we mentioned earlier.
Right. Operations must physically manifest the corporate goals.
Exactly. If the corporate strategy is to sell millions of identical ultra-cheap pens, your operations strategy cannot be built around highly customized, handcrafted artisanal assembly techniques.
Yeah, that would be a complete disaster. The entire operational foundation must be engineered for, like, ruthless cost-cutting and massive volume.
Right, they have to align.
That feels obvious enough, align with the boss. But the second force, pushing in from the left, is where I think things start to get chaotic. Market demand.
Oh, market demand is a relentless, unforgiving force.
Because it's what the customers actually want, right?
Yeah.
And more importantly, what they're willing to open their wallets and pay for.
Precisely. You might have a perfectly aligned corporate and operational strategy to build, say, standard gasoline cars efficiently.
Okay.
But if the market suddenly shifts and demands electric vehicles with highly complex software interfaces and, massive touchscreens,
Your operations strategy has to pivot rapidly.
it has to. If you don't adjust to satisfy that new demand, your perfectly efficient factory just becomes a museum of obsolete technology overnight.
But you can't just, snap your fingers and suddenly build electric vehicles.
No, you absolutely cannot.
Which brings us to the third force, pushing back from the right side. Resources, capabilities, and limitations. This feels like the ultimate reality check.
It really is. It is the physical and financial gravity of the company. And honestly, this is the tension that breaks so many ambitious startups.
How so?
Well, the market demand on the left might be screaming for same-day delivery of fully customized, highly complex products.
And the corporate board might be demanding it too. Give the people what they want.
Exactly. But your right arrow, your resources, dictates what is actually possible.
Right, you simply might not have the capital to build 50 new distribution centers.
Or you might not have the engineering talent. You might not have the proprietary technology required.
So operations strategy is essentially the art of breaking bad news to the CEO.
That's one way to look at it.
Like saying, I know the market wants this, but the laws of physics and our current bank accounts say we can't do it yet.
Sometimes, yes. Or, more accurately, it's the art of figuring out how to build those capabilities over a 5-year horizon so you can eventually give the market what it wants.
Okay. Balancing ambition with physical reality.
Exactly. It's a roadmap.
And what about the fourth force? The one pushing up from the bottom?
That is operations experiences.
Experiences. Like past projects.
Right. It represents the institutional memory of the company, the lessons learned from past successes, and crucially, past failures.
Give me an example of how that plays out.
Let's say 5 years ago, the company tried to implement a highly automated robotic assembly line.
Sounds great on paper.
But it was an absolute disaster because the workforce wasn't properly trained and the supply chain couldn't deliver parts fast enough to keep the robots fed.
So they just burned millions of dollars.
Yep. So that historical scar tissue has to inform the new strategy. You don't just blindly try the exact same thing again.
Right. You integrate the experience.
Exactly. You balance all four forces.
So you have corporate goals, market demand, internal limitations, and past experience. If you actually manage to balance all of those without going crazy, you then have to figure out had to actually execute.
Yes, you have to physically make the thing.
How do you trigger the physical making of a product? I'm assuming there's like a fork in the road here for most companies.
A massive fork in the road. It determines the entire organizational structure of the business.
Okay, let's get into it.
It really comes down to a philosophical battle between push environments and pull environments, or, to use the formal industry terms, forecast-driven versus demand-driven supply networks.
Let's start with push, because I feel like this is how most of us naturally assume the world works, right?
Yeah.
You guess what people want, you make it, and you put it on a shelf.
That is the absolute essence of a forecast-driven push system.
Yeah.
In this environment, every schedule, every material purchase, every factory shift is based purely on historical data and predictive forecasting.
So you're just looking backward to guess the future.
Right. You analyze past trends, maybe you look at macroeconomic indicators, and you predict that next quarter you will sell exactly 100,000 units of a specific television.
So you push the raw plastics and electronics into the factory, you push the assembled TVs onto cargo ships, and you push the boxes into retail warehouses.
Yes.
All entirely based on a highly educated guess.
And that guessing game introduces a terrifying vulnerability into the supply chain.
Which is what?
Unstable demand. I mean, if your forecast is perfectly right, it's a beautifully efficient system.
But consumers are fickle.
Incredibly fickle. Pandemics happen, viral social media trends happen, and when demand fluctuates even slightly from the forecast in a push system, it triggers a devastating phenomenon.
The bullwhip effect.
Yes, the dreaded bullwhip effect.
I have seen references to this destroying massive multi-billion-dollar companies, like the famous tech hardware crashes in the early 2000s. I want to really break down the mechanics of this for the listener. How does a tiny shift in consumer demand tear a global supply chain apart?
Well, think about the physics of an actual bullwhip.
Okay.
The person holding the handle only has to flick their wrist a few inches, right? A tiny movement.
Right.
But as that energy travels down the long, tapering leather of the whip, the wave amplifies. By the time it reaches the tip, it's moving fast enough to break the sound barrier.
The crack of the whip.
Exactly. In our supply chain scenario, the handle of the whip is the consumer at the retail store.
And the tip of the whip is the raw material supplier deep in the supply chain.
Precisely.
Okay, so let's walk through a scenario. Let's say a local electronics retailer normally sells 10 high-end gaming monitors a week. That's their baseline forecast.
Okay, 10 monitors.
But one week, a popular video game streamer reviews the monitor, and suddenly the store sells 15. A 5-unit increase.
Just a tiny flick in the wrist at the handle.
Right. Now watch how the wave amplifies. The retailer sees a 50% jump in sales, and human psychology kicks in.
Because the store manager doesn't just want to replace the 15 they sold.
Exactly. They want to make sure they don't run out if this trend continues. So instead of ordering their usual 10 from the regional distributor, they order 20. Just to be safe, build a little safety stock.
So the wave is getting bigger. The distributor gets the order for 20.
Right.
And the distributor isn't just looking at one store. They might be seeing this slight bump across a few stores in the region.
Right, so they start panicking too.
Exactly. They look at the sudden order for 20, which is double the historical baseline. The distributor thinks, wow, the market for these monitors is absolutely exploding.
So when the distributor places their order with the manufacturer,
they don't just order 20. They want to ensure they have enough buffer to handle this massive perceived boom. They order 40.
Oh my gosh. So a 5-unit increase at the actual cash register has already become a 40-unit demand on the factory.
And it gets worse.
How does it get worse?
The manufacturer receives this massive, unprecedented order for 40 units. They panic. They realize their current production lines cannot handle a 400% increase in baseline demand.
Right, the factory is scaled for 10.
So they spin up emergency extra shifts, they pay exorbitant overtime wages, and they contact their raw material suppliers.
The people making the raw plastic and mining the rare earth metals for the screens.
Yes. And the manufacturer orders enough raw materials to build 80 monitors, completely overcompensating to ensure they never face a stockout during this quote-unquote boom.
Wow. That is the tip of the whip cracking. An order for 80 units hits the raw material supplier, all because 5 extra gamers bought a monitor on a Tuesday.
And here is the real tragedy of the push system. By the time the raw materials were mined, the factory pays the overtime to build the 80 monitors, and they ship them across the ocean.
So like 3 months later.
Exactly. And the video game streamer has moved on to a different monitor. The consumer demand at the retail level has dropped right back down to 10 a week.
And now the entire global supply chain is absolutely choked with excess, wildly expensive inventory that literally nobody wants to buy.
Yes, the retailer marks it down, destroying their profit margin, and the manufacturer is stuck with warehouses full of unsold goods.
That is the bullwhip effect.
Yeah,
It is the ultimate nightmare of relying purely on forecasting in a volatile world.
it really is. And it's the primary reason why modern operations strategy is desperately trying to transition toward the alternative.
Demand-driven environments?
Or pull systems.
Yes, pull systems.
So if a push system is cooking a massive, expensive buffet and just praying that exactly 100 people walk through the door, a pull system must be more like a high-end, made-to-order restaurant.
Conceptually, yes.
You don't put the steak on the grill until the customer is sitting at the table and explicitly asks for the steak.
Exactly. The goal is to slash inventory risk while maintaining absolute customer satisfaction. You stop guessing and you start reacting to real confirmed demand.
But applying a restaurant analogy to a global supply chain reveals a massive physical problem, doesn't it?
It does. I mean, if a customer clicks buy on a laptop, you can't then start mining the aluminum for the chassis. The customer won't wait 6 months.
Right. You cannot have a 100% pure pull system from the dirt to the living room. It's physically impossible with global lead times.
So how does a massive enterprise actually pivot to a demand-driven model without their shelves constantly being empty?
The source material highlights two critical mechanisms to make pull systems work at scale.
Okay, what's the first one?
The first is replacing isolated forecasting with extreme bi-directional visibility.
Meaning everyone shares their data.
Yes, the manufacturer, the distributor, and the retailer have to share data instantaneously.
Oh, I see. If the manufacturer can literally see the cash register data in real time, they see that only 15 monitors sold.
Exactly. They don't have to rely on the distributor's panicked, inflated order of 40. They see the truth.
The text also mentions visibility regarding promotions, which seems like a huge blind spot.
Oh, it's a massive blind spot. Let's say the retailer decided to run a 50% off Black Friday sale on those monitors.
Right.
If they don't tell the manufacturer just sees a huge spike in sales and thinks it's a permanent market shift.
And they fire up the factory.
But if there is visibility, the manufacturer knows the spike is artificial and temporary, and they don't spin up extra factory shifts. They ignore the noise.
Okay, so extreme data sharing is step one. What is the second mechanism? Because you still have that lead time problem of mining raw materials.
The second and arguably most revolutionary concept is DDMRP.
DDMRP, Demand-Driven Materials Requirements Planning.
Yes. And the core innovation of DDMRP is the use of dynamic strategic inventory buffers.
Okay, let's really dig into this.
Yeah.
What is a dynamic strategic buffer? Because it sounds like corporate speak for just hiding extra boxes in the back room.
It's not at all. It is highly calculated. Instead of pushing massive amounts of finished inventory all the way to the retail shelf based on a long-term forecast,
Right.
you strategically place small, carefully calculated piles of inventory at very specific critical points along the supply chain.
And these are known as decoupling points, right?
Exactly, decoupling points.
Meaning they break the chain so the bullwhip wave can't travel through it.
Yes. Think of them as high-tech shock absorbers in a car's suspension.
Oh, that's a good visual.
If a car hits a massive pothole, representing a sudden spike in customer demand, the shock absorber compresses.
And the frame of the car, which is the rest of your supply chain, doesn't feel the violent jolt.
Exactly. The buffer absorbs the shock. You fulfill the sudden customer order immediately from the buffer without passing a panic signal all the way up the chain to the raw material suppliers.
And the dynamic part means these buffers aren't just like static piles of dust-gathering inventory.
Right. The system then simply acts to replenish that specific buffer back to its designated level based on actual realized consumption.
So it only replaces what was actually taken.
Yes. And the algorithms constantly resize the ideal level of that buffer based on rolling historical data and upcoming known events. It stops the violent system nervousness dead in its tracks.
But the reality of executing that, I mean, replacing gut-feeling forecasts with intense cross-company data sharing, real-time visibility, and complex algorithms, constantly resizing strategic shock absorbers across continents.
It's a lot.
You cannot run that system on a clipboard
Yeah.
or even like a basic spreadsheet.
You absolutely cannot. It requires an immense technological foundation.
Which perfectly transitions us into the next major pillar of operations strategy, technology choices. and balancing cost, efficiency, and agility.
This is where things get really expensive if you do them wrong.
This is where I see so many companies lose their minds. The shiny object syndrome.
Oh, yes.
A new technology drops, whether it's advanced robotics, Internet of Things sensors, or generative AI, and suddenly every executive wants it in their factory, regardless of whether they actually need it.
It's a huge trap.
So how does an operations strategy dictate choosing the right technology without just setting money on fire?
Well, the source material is remarkably strict about this. It provides a rigorous technology assessment matrix.
Okay, a matrix.
It dictates that you must evaluate any new process technology against 5 specific, unyielding priorities. You don't buy tech because it's new. You buy it because it delivers measurable improvements in one of these 5 areas.
Let's explore these 5 priorities because they seem like the perfect filter for any business investment. Priority number 1, speed.
Now, if the justification for the new technology is speed, it cannot just be a machine that spins a gear faster.
It has to be more than that.
Yes. The effect must be a measurable improvement in overall throughput and, critically, information sharing.
So faster data is often more important than faster motors.
Exactly. Can the technology take a demand signal from the retail store and transmit it to the factory floor in milliseconds instead of days? That is true speed.
Okay, priority 2, dependability.
Technology focused on dependability is all about removing chaos. It should enhance coordination and create immediate feedback loops.
Like what? Give me a factory example.
Imagine automated optical sensors on an assembly line. Instead of a human inspecting every 100th part, the sensor inspects every single part at the microscopic level.
Wow, every single one.
Right. And if it detects a flaw, it immediately shuts down the line. It ensures that the outcome is perfectly predictable.
It prevents you from making 1,000 defective parts before anyone notices. That makes total sense. Priority 3, flexibility. I imagine in a volatile market, this is paramount.
Flexibility is perhaps the most strategic advantage a company can buy today.
Because it lets you pivot, right?
Yes. Flexible technology allows a facility to scale production volume up or down radically without suffering massive financial penalties, but it also means rapid changeovers. Yeah, so if a traditional stamping press takes 3 days to manually reconfigure from cutting car doors to cutting truck beds, that is highly inflexible.
Right, that's 3 days of downtime.
But if a new robotic cutting system allows you to change the specs with the push of a software button and 0 downtime, that technology provides massive strategic value. It lets you pivot with market demand instantly.
Priority 4 is quality.
Quality tech drives standardization. It removes the variability of human fatigue.
Right, people get tired, robots don't.
Exactly. It ensures that the millionth unit off the line is structurally and aesthetically identical to the first unit off the line.
And finally, the universal constraint. Priority 5, cost.
The technology must create efficient and effective processes, whether direct manufacturing processes or indirect administrative ones, that ultimately lower the total cost of operation over its entire life cycle.
So you run the shiny new tech through those 5 priorities. But the text includes a fantastic, almost philosophical warning here.
It does.
It says verbatim, avoid gut feelings or bias toward new technologies without establishing need.
It's so true.
Think about how guilty we all are of this in our personal lives. You buy the newest smartwatch with blood oxygen sensors and satellite tracking just because the commercial looked amazing.
Right.
Not because you ever actually established a genuine need to track your blood oxygen while hiking in the Himalayas. Because you don't hike in the Himalayas.
Consumers waste hundreds of dollars on that bias, but corporations waste hundreds of millions.
Yeah, the scale is wild.
They hear buzzwords at a conference. Blockchain, AI, digital twins, and the board demands implementation without ever identifying the specific operational problem those tools are meant to solve.
So the APSCS framework demands a cold, evidence-based assessment.
Absolutely cold.
How do they enforce that? What are the actual steps to prevent a CEO from just buying a fleet of autonomous warehouse robots on a whim?
It's a rigid methodology. First, you assess the total benefits against the potential downsides and implementation risks.
Okay, a basic cost-benefit analysis.
Second, you gather hard empirical data on the expected improvements to those 5 priorities we just discussed.
So you can't just say, it'll be faster.
No, you cannot just write a memo saying, the robots will make us faster. You must prove exactly how many seconds will be shaved off the cycle time.
Wow.
Third, you conduct a brutal financial impact assessment. What is the exact return on investment, and what is the specific timeline for that return?
And if it actually survives all that math, you still don't roll it out globally, right?
Yeah.
The final step seems to be the most crucial safety net.
Always, always execute a pilot program before committing.
Tapped it first.
You test the technology in a highly controlled, isolated environment. You do not rip out your entire existing factory infrastructure on day one based on a vendor's promise.
Because operation strategy is about long-term survival.
Exactly. You cannot risk the entire company's capability on an unproven technological hypothesis.
I love the theory here, but I really want to see what this looks like in the mud and the dirt of a real industrial environment.
Let's look at the case study.
Yes, we have an incredibly detailed example in the sources. The Shipbuilder Technology Roadmap, a multi-year plan to drag a massive traditional manufacturing operation into the modern era.
This roadmap is one of the most illustrative pieces in the entire curriculum.
It really is. It maps out a massive technological evolution for a commercial shipbuilding company across 3 distinct years.
And it categorizes the evolution into 5 streams: the business goals, the product itself, the ships, the process of making them, the equipment used, and the underlying software.
Let's dissect this roadmap because the sequence of events is fascinating. Walk us through year 1. The text refers to this as the foundation. What is the shipyard actually trying to achieve in year 1?
In year 1, the business goal is remarkably humble. It is simply to meet the existing budget and the existing schedule.
Wait, really? That's it?
That's it. They are not trying to revolutionize the industry yet. They just need to execute their current baseline plan without failing while they install the new technology.
But the equipment and software categories in year 1 are where the physical work happens. What are they installing?
This is where they lay the plumbing. Under equipment, they are deploying workers to physically install QR codes on thousands of small, untracked assets across the massive shipyard.
Basically putting a barcode on everything.
Yes, and they're retrofitting their heavy equipment, the massive cranes, the welding stations, the transport vehicles with active RFID tags.
Okay, tracking the big stuff.
And under software, they are developing what the text calls a blockchain minimum viable product, or MVP.
Okay, I have to stop you there. QR codes and RFID tags make perfect sense. You need to know where your wrenches and cranes are. But a blockchain MVP.
I know how it sounds.
Isn't blockchain just the underlying architecture for cryptocurrency? What business does a shipyard have building a blockchain? That sounds exactly like the shiny object syndrome we just talked about.
It definitely sounds like it, but in high-stakes supply chains, blockchain has a very specific non-financial utility. It acts as an immutable, unhackable ledger of provenance.
Provenance, meaning the origin and history of a part.
Precisely. Imagine you are building a massive commercial ship. It uses thousands of specialized high-grade steel valves to manage internal pressure.
Okay.
If one of those valves is a cheap counterfeit knockoff that sneaks into the supply chain, the ship could literally sink.
Oh, wow. That's catastrophic.
A blockchain MVP in this context is a pilot software program where the digital identity, the metallurgical testing results, and the chain of custody for every single critical valve is permanently recorded on a decentralized ledger.
So nobody can fake the paperwork.
Exactly. No supplier can alter the records to hide a failed safety test.
So it's the ultimate paper trail baked into the software. That makes total sense. And looking at year 1, what really stands out to me is the restraint.
Yes, the discipline is key.
They are installing QR codes and building a basic ledger. They aren't trying to use, like, artificial intelligence to automate the cranes yet. It's literal grunt work.
Because you cannot run advanced analytics if you do not have reliable data. The QR codes, the RFID tags, the blockchain ledger, these are simply mechanisms to create clean, reliable data streams.
You have to lay the sensory nervous system before you can give the factory a brain.
Exactly.
So they survive year 1. The foundation is laid. Everything is tagged. We move to year 2, which is focused on integration. How do the goals elevate?
Now, the business goal shifts from just surviving the budget to actively meeting asset utilization goals.
Because they can finally see their assets.
Right. Because they tagged all the heavy equipment with RFID in year 1, they now have a year's worth of data on how often those cranes actually move. They can start ensuring the equipment is used efficiently rather than sitting idle.
And how do the operational processes and software evolve to support that?
Under process, the workforce begins to develop and train for predictive maintenance.
Predictive maintenance, not waiting for it to break.
Exactly. Instead of waiting for a generator to break, they are learning how to read the data to fix it before it fails. And under software, they launch what the roadmap calls Release 1, which are the equipment RFID interfaces.
Meaning the software is finally talking to the hardware.
Yes. A manager can finally look at a digital backboard and see the exact real-time location and status of every single piece of heavy machinery in a 500-acre shipyard.
But again, look at the discipline. In year 2, they're only training for predictive maintenance. They aren't fully relying on it yet.
They're taking it slow.
It proves that a true operations strategy requires immense patience. You simply cannot compress a 3-year technological and cultural evolution into a 6-month sprint without completely breaking the morale of your workforce and the integrity of your systems.
If you try to force predictive maintenance algorithms on day 1, before the RFID tags are installed and the interface software is tested, the algorithm has no data.
It's trying to predict the weather in a windowless room.
Perfectly said.
Which brings us to the payoff. Year 3, optimization. What happens when the plumbing is finally connected to the faucet?
In year 3, the business goal leaps to break-even analysis and total asset optimization.
They're finally making real money from the tech.
And because of the tedious foundation laid in years 1 and 2, the product goal, the actual delivery of the massive ships, finally sees enabled compressed project schedules.
Well,
Because the system is so efficient, they can physically build and deliver the ships faster than ever before.
and the equipment and software categories reflect that maturity, right?
They do. Under equipment, they are no longer just tracking assets. They are actively adjusting equipment levels based on internal demand patterns. They know exactly how many welders they need on a Tuesday in November.
That's incredible.
And the software hits release 2, analytic interfaces. This is the advanced AI and analytics that finally utilizes the massive lake of data they've been collecting for 2 years.
That roadmap is brilliant. It takes all the abstract theory of the technology matrix and proves that real transformation is phased, evidence-based, and deeply sequential.
It's a textbook execution.
Okay, so let's synthesize where we are in the journey. We've established the overarching strategy balancing the 4 forces.
Check.
We've chosen our organizational structure, push versus pull, utilizing dynamic buffers to kill the bullwhip effect.
Check.
And we've rigorously selected and roadmapped our technology investments to ensure we aren't just buying shiny toys. We have the plan, the system, and the tools.
So what's left?
Right. What does the actual physical factory floor look like? When you walk into the building, where do you physically bolt the machines to the concrete?
This is where operations strategy translates into pure physical geometry. We are moving into manufacturing environments, process types, and layouts.
Okay.
And the fundamental concept that governs every single physical decision on a factory floor is known as the product process matrix.
The source text sets this up as the ultimate, inescapable trade-off in all of traditional manufacturing.
It really is.
It's visualized as a graph. On one axis, you have volume, how many units you are producing. On the other axis, you have variety, how highly customized or unique those units are.
And the brutal truth is that historically you cannot have both. It is an inverse relationship.
Give me an example of that trade-off.
If you want extremely high variety, meaning every single product you make is entirely unique to the customer's exact specifications, you are going to suffer from very low volume.
Because it takes time to customize.
You simply cannot build a million unique things quickly. Conversely, if you want incredibly high volume, pumping out millions of identical units a day at a very low cost, you must ruthlessly sacrifice variety.
Based on where a company decides to sit on that matrix, the material defines 4 distinct manufacturing environments. This is a fascinating spectrum. Let's walk through it, starting at the extreme end of low volume and high variety.
That environment is ETO, engineer to order.
Engineer to order. Think of a company that builds custom communications satellites or specialized suspension bridges or massive one-of-a-kind industrial power turbines. Every single product is completely unique.
And because it's unique, the lead time, the amount of time the customer has to wait from the moment they sign the contract to the moment it's delivered is the longest of all the environments.
Easily the longest.
The text maps the timeline out. It starts with designing the product from scratch, then purchasing the highly specialized raw materials, then production, assembly, and finally shipping. The customer is waiting through all 5 of those stages.
Sometimes for years.
Wow.
Yes. And from a management perspective, the primary control focus in an ETO environment is constantly adjusting your workforce capacity to customer needs.
Because you don't know what you'll need tomorrow.
Right, because you don't know what the next order will look like. You can't have a rigid, automated assembly line. You need highly flexible engineers, specialized craftsmen, and versatile workspaces that can adapt to entirely new designs on the fly.
Okay, so let's slide one step down the matrix. We increase the volume slightly, and we decrease the extreme variety. We arrive at MTO, make to order, which is sometimes called configure to order.
In an MTO environment, you are no longer engineering from a blank sheet of paper.
So you save the design step.
Exactly. You have a portfolio of standard designs, but you offer unique configurations of those standard features.
Like ordering a car.
A classic example is ordering a high-end luxury car. You don't ask them to invent a new engine, but you do pick the specific paint color, the type of leather interior, the stereo system, and the wheel package from a vast list of options.
Because the engineering is already done, the lead time shrinks significantly compared to ETO. The starting point for the manufacturer isn't a design desk. It's raw material inventory. The customer waits through production, assembly, and shipping.
And the management control focus shifts from pure engineering capacity to adjusting those complex configurations to meet specific customer needs without slowing down the initial production phases.
Moving further down the matrix, increasing volume again, and stripping away even more variety, we hit ATO, assemble to order.
This is the environment I think we interact with most often in daily life.
What are some examples?
The classic ATO examples are a fast food hamburger or a standard customized desktop computer.
Okay, so the parts are already there.
Yes. The raw materials have already been processed into standard components long before you place your order. The burger patties are cooked, the buns are staged, the computer motherboards are built, the hard drives are formatted.
So the lead time shrinks dramatically again. The process doesn't start with raw materials. It starts at WIP inventory work in process components.
You're just putting the pieces together.
Right. The customer is only waiting for the final assembly and shipping phases, putting the Lego blocks together.
Precisely. And the control focus here is entirely on meeting manufacturing assembly schedules and precise delivery dates. You just have to assemble the pre-made modules fast enough to keep the customer happy.
Which brings us to the final extreme, on the far end of the matrix. Massive volume, zero variety. MTS, make to stock.
This is your toothpaste, your standard rolls of toilet paper, basic ballpoint pens.
Things you just grab off a shelf.
Yes. The product design is completely rigidly fixed. The factory produces millions of identical units to standardized stock-keeping units or SKUs.
The lead time for the consumer here is basically zero. You walk into a store and it's there. Production and assembly happen weeks or months before you even realize you needed toothpaste.
The process starts at finished goods inventory.
And the control focus in an MTS environment is entirely divorced from individual customization. The focus is purely on ensuring customer service levels.
Which is an operational term meaning making absolutely sure the retail shelf is never, ever empty.
So that is the traditional spectrum, engineer to order down to make to stock. But what I find fascinating is that modern companies are not satisfied staying in their lane.
No, they want it all.
They are constantly trying to cheat the rules of this matrix. They want the massive profit margins and customer delight of make to order, but they desperately want the low costs and operational efficiencies of make to stock.
And the source material highlights several brilliant hybrid models where companies are successfully hacking the matrix.
Hack the matrix.
Yeah, mass customization is the holy grail for many consumer brands today.
How does that actually work? Because it sounds like an oxymoron. Mass customization.
Mass customization is the ability to offer highly customized products at nearly the same cost and speed as a high-volume MTS process.
Okay, give me a real-world example.
Think of customized athletic shoes like the Nike by You program. You design a totally unique colorway for your sneakers online.
Right.
Historically, a custom shoe would be a slow, expensive make-to-order process. But by utilizing incredibly flexible technology like modular digital cutting machines and advanced automated routing, they introduce high variety into a high-volume factory without stopping the line.
That is incredible. The text also details another strategy called postponement. The definition is delaying final differentiation for less inventory and faster response.
It's a very clever strategy.
I'd love a concrete visualization of how a company uses postponement to cheat the matrix.
Postponement is a brilliantly elegant solution to global supply chain risk. Let's look at a company that manufactures power supply bricks for consumer electronics laptops, for instance.
Okay.
They sell these globally, but different regions have entirely different physical electrical plug standards. The US has flat prongs, the UK has large rectangular prongs, Europe has round pins.
Right. So if they operate as a pure make-to-stock environment, they have to use forecasting.
They have to guess exactly how many UK plugs and European plugs they will sell next quarter and build them all at their primary factory in Asia.
And as we learned earlier with the monitors, forecasting is dangerous. If they guess wrong, they suffer the bullwhip effect.
They end up with warehouses full of useless UK plugs, while European customers face massive back orders.
So how does postponement actually solve this?
Instead of building finished, region-specific chargers at the factory, they redesign the product into two pieces: a generic universal power brick and a small, detachable, region-specific plug.
Ah, okay.
The massive factory in Asia operates as a pure, high-volume, make-to-stock environment, churning out millions of identical, generic power bricks at an incredibly low cost.
Because it's exactly the same brick.
Yes, they ship massive crates of these generic bricks to regional distribution centers around the world.
And they don't attach specific plugs until they get there.
Exactly. They postpone the differentiation until the absolute last possible second. When a confirmed order comes in from a retailer in London, the workers at the UK distribution center simply snap the UK plug onto the generic brick and ship it.
That is so smart. It slashes the inventory risk of forecasting wrong, but maintains the incredibly fast response time and low production cost of mass manufacturing.
That is such a clever operational hack. Keep the mass production efficiencies for 95% of the product and only customize the final 5%.
This relies heavily on what the text calls modular design, right? Standardizing the product into interchangeable modules.
Yes. Modular design is often more expensive and complex for the engineers to design up front, but it makes the assembly and maintenance infinitely simpler, and it forms the entire physical basis for assemble-to-order and postponement strategies.
So we understand the volume and variety trade-offs and the clever ways to manipulate them. But we still need to build the physical factory.
Right, the actual layout.
Based on where a company sits on that matrix, the source material dictates that the actual process type and the layout of the building must align. The text outlines 5 specific process types.
And these map beautifully to the environments we just discussed. At the extreme high-variety, low-volume end, you use a project process type.
Projects, okay.
These are unique deliverables, usually physically large and highly complex, with a specific deadline. The management control here doesn't focus on line speed, it focuses on time, cost, and scope management.
Stepping down the matrix, you have the work center process type, which is traditionally known as a job shop.
In a work center, the factory floor is divided by common functions. You have highly skilled, versatile workers. The flow of materials is intermittent and highly variable because every custom order takes a different physical routing through the shop.
Which leads to bottlenecks, right?
It leads to unbalanced workflows and a very high level of work-in-process inventory, because a half-finished product might just sit on a cart for 3 days, waiting for a specific machine to free up.
Next is the batch process type.
Batch operates at a higher volume than a work center. Machines are still grouped by function, but you are running larger batches of identical parts.
So it's a bit more efficient.
Because the runs are longer, you have fewer machine changeovers and setups. The worker skill level required is moderate rather than highly specialized.
Then we arrive at the line process type. This is the classic Henry Ford vision of manufacturing.
High volume, strictly controlled rates, discrete units moving sequentially. The skill level required from the worker is usually medium to low because the work is highly subdivided into repetitive, easily learned tasks.
But it's inflexible.
It is incredibly ruthlessly efficient, but it is entirely inflexible. A line is designed to make one specific product. If you invent a new product, you usually have to pour new concrete and build an entirely new line.
And finally, the most extreme volume process, continuous.
Continuous processes aren't for discrete items like cars or phones. They are for liquids, gases, or bulk solids.
Like an oil refinery.
Think of an oil refinery, a chemical plant, or a massive paper mill. Dedicated work centers process material in an unending end-to-end flow. It runs 24 hours a day, 7 days a week. It is massively inflexible, but it operates with extreme precision and the lowest possible per unit cost.
Okay, those are the theoretical processes.
Yeah.
But the text then gives us 4 actual physical layout choices to house these processes. Fixed position, functional, cellular, and product-based.
The physical geometry.
I'd love to paint a vivid mental picture of these for the listener, exploring the pros and cons of how you arrange the real estate. Let's start with fixed position.
In a fixed position layout, the product itself never moves. It is either too massive, too heavy, or too fragile to be pushed down an assembly line.
Think back to the shipbuilder we discussed earlier.
Oh.
Or an aerospace company building a commercial airliner.
Exactly.
The benefits listed for this layout are high flexibility in how you attack the work, and obviously low material movement for the product itself. But the limitations sound like a logistical nightmare.
They are. Because the product doesn't move, you have to bring the entire factory to the product.
Wow.
It requires immense effort and coordination to constantly move specialized, heavy machinery, hundreds of workers, and massive amounts of raw materials to the exact location of the build.
And you probably don't have much space.
Furthermore, you have incredibly limited storage space. You can't store thousands of steel plates right next to the ship. They get in the way of the cranes. So the choreography of delivering parts just in time to a fixed position is staggering.
Next is the functional layout. This aligns with the work center or job shop process we discussed. You group all the equipment by machine type. All the welding machines are in the north wing. All the drill presses are in the south wing.
It's highly compartmentalized by function.
Let me offer an analogy here. A functional layout feels exactly like a massive, traditional commercial kitchen. All the ovens and bakers are segregated in the baking zone. All the deep fryers are in the fry zone.
That is a perfect visualization.
And the benefits of that functional arrangement are significant. You have very high equipment flexibility. Because all the ovens are in one place, they can be shared across every single dish on the menu.
You need fewer ovens overall.
Right. And crucially, you have a very low risk of a machinery breakdown stopping the entire operation. If one drill press breaks in the drill department, you don't stop the factory, you just roll the part over to the functional drill press right next to it.
But the text outlines some brutal limitations for this layout. It notes that queue time leads to much higher total production time.
In our kitchen analogy, the chopped vegetables might just sit on a tray for 20 minutes in a queue waiting for a sauté pan to become available.
You have high bottleneck potential. And the handling costs are atrocious because you are constantly moving the product back and forth across the entire facility.
Yeah, that makes sense.
A part might go from drilling across the factory to welding, back across the factory to be drilled again, and then over to painting. The flow lines drawn on a map would look like a tangled plate of spaghetti.
Which is exactly what prompted the lean manufacturing revolution to champion the next layout type, the cellular layout.
The cellular layout. The text says this involves grouping machines into product families.
If the functional layout is the massive, chaotic commercial kitchen, how would you describe a cellular layout?
A cellular layout is a food truck.
Oh, I love that. Let's break that down.
Think about the interior of a high-volume taco food truck. The worker doesn't have to walk to the oven department in the back to heat a tortilla, and then walk across the truck to the chopping department to get onions.
Everything is right there.
Everything required to build that specific product family. The tacos is arranged in a tight, highly optimized, usually U-shaped cell. The grill, the meat station, the tortillas, the salsa, it is all within arm's reach of one or two cross-trained workers.
They pull a raw tortilla in one side of the U, and a finished wrapped taco comes out the other side seconds later.
The benefits outlined in the Apex S material make perfect sense when you picture the food truck. It vastly minimizes material handling distances and floor space requirements. Processing time is lightning fast.
And most importantly, almost no work-in-process inventory accumulates.
The taco doesn't sit half-finished waiting in a queue. It moves fluidly from start to finish. Lead times shrink dramatically.
But it is not a silver bullet, right? There is a major limitation.
A cellular layout only works if your products can actually be grouped into logical, similar product families with identical process routings.
So you can't just make anything.
You can easily make burritos in the taco cell. But if a customer suddenly orders a highly complex, multi-tiered wedding cake, the cell completely falls apart.
Yeah, you don't have the space, the right tools, or the routing to make a wedding cake in a taco food truck.
If your product variety is too wild, cellular manufacturing becomes impossible.
Which leaves us with the final layout, the product-based layout. This is the pure, continuous assembly line.
The product moves smoothly down a conveyor belt, and the workstations are arranged in the exact sequential, chronological order of assembly. Step 1, Step 2, Step 3, in a perfect straight line.
The benefits here are all about scale and speed. You achieve the lowest possible total material handling costs because the conveyor belt does the moving.
Production control is incredibly simple. You just manage the speed of the belt. Production time per unit is minimized, and equipment utilization is near 100%.
But the limitations are severe. You have extremely limited flexibility to change the product design.
And the biggest, most terrifying risk for a plant manager, a single machine breakdown anywhere on that line shuts down the entire multi-million-dollar operation.
Right.
If workstation number 4 jams, workstations 5 through 20 instantly have nothing to do, and workstations 1 through 3 get backed up and have to halt. The vulnerability is total.
It is all a massive, high-stakes game of trade-offs. Speed versus flexibility,
Yeah.
cost versus quality, volume versus variety.
Absolutely.
And listening to all of this, it brings us perfectly full circle to where we started our conversation today. Every single micro decision, whether to tear down a functional kitchen layout and build food truck cells, whether to invest in an RFID tracking roadmap or stick with cheap barcodes.
Whether to aggressively push inventory based on predictive forecasts or implement complex DDMRP dynamic buffers to pull it,
All of those granular decisions must seamlessly roll up and align with the four forces of the operation strategy, which in turn must flawlessly serve the ultimate corporate strategy.
because if the overarching corporate strategy is to sell millions of identical, ultra-cheap items, and your operations manager decides to build a highly flexible cellular layout utilizing expensive, customized 3D printing technology, the company will tear itself apart from the inside out. The alignment must be absolute.
This has been an incredible journey through the hidden architecture of the business world. We started in the abstract heights of the boardroom, dissecting how a true operations strategy demands a 5-year time frame and a broad perspective.
Balancing corporate ambition with the gritty reality of market demand, physical resources, and the scars of past experience.
We then explored the critical systemic pivot away from the dangers of push systems and their devastating bullwhip effects.
Diving into the mechanics of demand-driven pull systems that rely on extreme visibility and strategic shock absorbers.
We tackled the ever-present danger of the shiny object syndrome, learning the disciplined, rigid APC's matrix for assessing technology investments based on measurable improvements to speed, dependability, flexibility, quality, and cost.
Using the incredibly patient, multi-year shipbuilder roadmap as our guide for how real transformation actually happens.
And finally, we translated all of that abstract strategy into the physical reality of concrete and steel, mapping out how the inescapable tension between volume and variety dictates exactly how a factory is built, from a fixed-position aerospace hangar to a high-speed, continuous make-to-stock assembly line.
It is a massive amount of incredibly dense operational theory to absorb.
But as we established at the very beginning, understanding this material gives you a profound new lens through which to view the global economy. When you read about a massive shipping delay or a chip shortage in the news, you don't just see bad luck anymore.
You understand the mechanics of the bullwhip effect that amplified it?
When you purchase a remarkably cheap yet highly customized product online, you aren't just a consumer. You now understand that they are actively hacking the product process matrix using advanced postponement or modular design.
You are quite literally seeing the matrix behind the commerce.
And that is why this material matters. Knowledge is only truly valuable when you can apply it to decipher the chaotic world around you. This operational lens strips away the corporate jargon and reveals the hard, physical logic of how human beings actually build and deliver the modern world.
Very well said.
I want to leave everyone listening with a final, somewhat provocative thought to mull over. We talked extensively about the product process matrix and the brutal historical trade-off that has governed manufacturing for a century: volume versus variety. You can't have both.
Historically now.
But as artificial intelligence grows exponentially smarter, as industrial-scale 3D printing, advanced robotics, and hyper-flexible cellular layouts become drastically cheaper, will that traditional trade-off eventually disappear entirely?
That's a fascinating question.
Consider the implications. Will we soon live in a society where everything from our cars to our appliances to our clothing is a pure make-to-order environment, perfectly customized down to the millimeter for your specific needs, but manufactured and delivered at the blazing overnight speed and rock-bottom cost of a traditional make-to-stock assembly line?
It would change everything.
Think about how that total collapse of the volume and variety barrier would radically redesign not just the physical layout of global supply chains, but the entire physical world around us. The rules of business diagnosis are constantly evolving, and the boundaries of what is possible are expanding every day. Keep questioning how the world is built. Keep looking for the invisible strategy behind every physical product you touch. Thank you so much for joining us on this deep dive. We'll see you next time.